I've fallen and I can't get up.
So the first thing you want to do is turn on your Spiderbot. Okay, so now it's on. You can see the lights are on. Then you wait for the Spiderbot network name to show up. So in this case, it's ESP32 Spiderbot. Connect to it. Alright, so to check that it's connected, we hit the refresh stream button. Okay, now we can see the camera stream. So now we adjust the camera stream so we can see the full picture. So zoom out. Okay, then we'll have to adjust with these arrows on the side. Adjust so you can see black bars. Okay, so there we go, full screen. So you can also test out. So headlight button obviously turns on headlight. The yellow bar here is for speed. So you want to adjust this while it's stopped, otherwise it kind of glitches out. The blue bar here is the walking height. So you have to hit stop first to send the first command, and then it will adjust based on commands after that, so we can adjust the walking height. Obviously there's forward, stop, reverse, strafe left, strafe right, forward, rotate right in place, rotate left in place. We have additional commands, say hi, and dance. Those are just fun actions. We have a calibrate servos, so that will set all servos from 0 degrees to 45 degrees. So you can use this when you're assembling the Spiderbot to ensure everything is at the correct angle it should be. Stop. And then at the bottom here we have the IP address. So that's the IP address of the ESP32. Since it's creating its own access point, it should be the same IP address every time. So you shouldn't have to adjust that. This is the Spiderbot bill of materials. So you can see here at the total, we have an estimated cost of 351 Canadian dollars. And you might think, well, that's kind of expensive, right? Well, if you have 18 servos in a robot and a servo controller to control them, it's going to be kind of expensive, because if you cheap out on those components, your Spiderbot will not work very well. And I've learned this from personal experience by just doing that. Buying cheap servos, buying cheap servo controller boards. And yeah, it will kind of work, but it will just be not as good quality. It's just spending a bit more money on getting high quality servos and high quality servo controller. But anyway, so we'll just go through the list real quick of everything on it. So obviously we have the ESP32 cam, the microcontroller that controls everything. You definitely want to get one that has a programmer board with it. That's USB. It will make your life a lot easier. The servo controller itself is the SSC32U. There's not much about to say about that. Definitely need that. So I use GoTech servos. They're like 2.5 kilograms of torque, I think. They're really good servos. They're very durable, which is important. So we're going to need a single pull, single throw switch to turn the Spiderbot on and off. We're going to need breadboard jumpers, just various ones for various connections. I would just recommend buying a whole pack of them, because it's always good to have those for really any project. We have our battery, just a regular 2000 milliamp 2-cell 7.4 volt battery. We're going to need a battery connector, so that just interfaces with the battery. We're going to need a voltage regulator, 5 volt 9 amp step down, and of course all the links here are right here for the items. We're going to need a capacitor, so that's for the bypass capacitor for the ESP32 cam. Make sure it doesn't brown out, especially with servos drawing a lot of power, potentially 18 of them. Servo cable extenders, I recommend getting some of these for the tibia motors or servo motors. So you're going to need 6 of them. 2-watt LED. This is optional, of course, the LED light bar, but I think it looks cool and useful for nighttime environments to have the LED. So the resistor, the transistor, the JST, those are all supporting the LED, so that can be controlled by the microcontroller. And of course we have our filament. So for this, pretty much the entire Spiderbot was printed with PAL filament, and TPU was also used, but only for the rubberized tips of the feet. The tools used for this project were a 3D printer, obviously to print all of the 3D printed parts. Precision magnetic screwdrivers, going to need those to screw in the servo screws. Soldering iron, we're going to need that for building the circuit and making those connections where necessary. Wire strippers, definitely to strip insulation and cut wires, and then pliers as well, may be useful for assembling and disassembling the parts of the Spiderbot. Brief overview of the slicer files for 3D printing. So we have the leg pieces here, some of them, and we can see that we use some organic supports for these pieces, the coaxas, and then we just use regular snug supports for the tibia. Next we have the body of the Spiderbot, the main frame. We have the organic supports used here for all these pieces here. That's what I would recommend to do. Here we have leg pieces, linkages, and connectors. See, all the connectors are round, so therefore they have supports. Here we have the top piece, the electronics mount. Some electronics mounts as well, and some linkage covers. So you can see here the pegs are supported vertically here for these electronics mounts. And last we have the tibia feet. So these are printed in TPU, that's why they have their own plate. On the document overview we have the 3D print list. So this just has all the part names as well as what material they should be printed in and some printing notes. The files are available for download at Maker World. The link is in the project overview. All right, we're going to start with the assembly of one of the legs. This will be repeated 6 times, mirrored twice. So 3 legs will be the same, 3 legs will also be the same, but they won't all be the same, but that's only because they were mirrored left to right. So first we want to start with our tibia piece, all right? And we have our tibia sock, okay? So that just slides into there like this. Should snap into place and be very hard for it to come off. Next we're going to want to put our servo in. So we have a servo already prepared with a servo extender. This is just because the normal servo cable length isn't long enough only for the tibia. So you only need these for the 6 of these for the tibia, which is this piece. So you want to install the servo with the head to the top, like furthest away from the rubber foot. It should slide in like so, kind of snap into place, especially the first time if you've never done it before. The newer model actually has, or the latest 3D model actually has a loop here for your cable to go through, just to keep it more managed, but it's not on this current piece. But you would do that if you printed out that version. So first, we're going to wrap our precision screwdriver here. We're going to screw in the servo mount screws. So these are the bigger ones. Okay, one down, and then the second one. They should line up with the hole that's already printed in there beforehand. All right, we have our servo installed. Get the femur connected, but we're not going to fully connect it. We're just going to connect it on one side. All right, so we'll have one of the connector pins here that's going to go into the side of this coxa piece. Then we have a snap connector that goes onto this. And then the other side of the snap connector goes onto the tibia. So for the tibia, you want to feed it through this loop right here. On the newer version, I think there's 2 loops. So just feed it through both of them. Pull it through. And there we have the assembly for now. The next step is to install the coxa servo on the frame of the Spiderbot. In this case, I already have all other 5 legs installed, but like I said, they're all mirrored. So first, we'll take the servo, will feed the end through this, I don't know, whatever it's called. Okay, pull it through. You can see. So now we're going to want to take the servo head and put it in this way. It should fit right into the square slot below. Might be a little tricky to get in there. It's easier if you go this way first, this end, like this, and then push it down. It should snap into place. So you can see here, the end of the servo head is closer to the edge. So now we'll just put our screws in, like before. Then you want to put the screw through this hole to reach the hole for the screw. It's going to be a little tricky. Alright, there we go. The servo is installed. Well, since we can't go any further with installing the servos, we have to assemble the body. That's because to go further with assembling the servos, we need to have them at 0 degrees in order to assemble them. Obviously, if your servo's not on and powered and set to 0 degrees, when you connect the parts on, 0 degrees won't be correct in terms of where the servo thinks 0 degrees is, so your robot won't work correctly, so that's important. Alright here, so just imagine these legs aren't installed yet, obviously other than the servo on the end here. So we have our main body here, so we're going to want to start with our battery. So this is a 3000 milliamp hour battery. So this one has a JST connector for charging. So I put this out of the front so it's easy to access. And then here is the main part we use, or the connector that we use to power the rest of the Spiderbot. So we'll set that in here. I have the circuit already assembled. You guys can figure this out from the circuit diagram. It's really very simple, but I'll just show you real quickly. So we have obviously the connector to the battery here. So the positive is connected to a single pole, single throw switch, which turns the Spiderbot on and off. And then the positive and ground, they're input into this 5 volt 9 amp step down voltage regulator. So both the servo board is connected and the ESP32 is also connected directly to the voltage regulator. I just don't have the ESP32 plugged in. For the ESP32 we have the capacitor here, the bypass capacitor that can prevent brownouts. As you can see here, we have it pretty close to the leads that connect to the 5 volt and ground on the ESP32. And as well here we have the BJT transistor that's used to toggle the headlight on and off. So yeah, first we'll connect the connector to the battery, like so. Make sure that's off as well. Make sure your switch is off. No need to have that on. The switch, so this one has a thread on it. So it goes through this little mount here at the back. So you just push it through. And then we're going to put the washer and the nut that comes with it on, just to hold the switch into place. Okay, so that's secured into place. So we have our upper electronics mount here. These pins are removable, but I recommend putting them in this configuration. You see there's the notch here on the front. This is just to allow the ESP32 to slide in and out, you'll see. So we want nothing to get stuck underneath when we pinch it together, so just make sure everything's clear. Might be annoying with all the wires and stuff. So yeah, that just snaps into place. It should line up directly with the piece below it. Okay, there we go. The battery's now encased there, it won't come out. And now we just have to mount our electronics. So for the voltage regulator, we have this custom holder. That's a snap-in. So it just slides into these rails right here. So we'll just put it in like this. See, it slides right into place, nice and secure. Actually, we need to adjust that. So I moved one of the pins to right here because it was in the way. Or I made a mistake. Okay, now the voltage regulator will plug into the end here with the snap-in connectors. There we go, nice and easy. And then the next part to plug in is the servo board. So we're going to put it in this way. I don't think it really matters that much either way. It would probably work. Just slides into place like so, holding it nice and secure. Make sure nothing's in the way. Then it just snaps into place. Okay, so now we have our electronics mounted. Don't forget to also connect your VL and your VS pins. So that is these two right here. They just connect the voltage for the servos and the logic voltage together because we're powering everything off 5 volts in this system. Okay. So next we're going to install our ESP32. Okay. So we have the special wire here, the 5 volt and ground with the capacitor. Going to connect that to 5 volt and ground on the ESP32, of course. We're going to connect the receive pin of the servo board to the transmit pin called UOT or U0T, whatever it is. And then we're going to connect our BJT transistor to pin 4. Just a note, pin 4 also activates the LED on the ESP32. I use pin 4 because my voltage regulator for it burnt out, so it doesn't work anymore. But if you want to keep that flashlight on and put it on a separate pin, you can just connect it to probably pin 16. You'll just have to change that in the software, but it's no problem. Okay, so once your 4 wires are plugged into the ESP32, it slides into the mount at the front. It should sit in there nice and snug and not come out. All right. Now the next step is to connect our servos to the board, and that will allow us to make sure they are connected at 0 degrees. So make sure you just follow your servo assignments. Yours may vary, but by default, they should be all the same. It depends what servo board you're using and whatnot, but if you're using this one, I would just recommend using the same pins. But you can just follow the pin assignments for figuring out exactly which one connects to what. But I'll just go ahead and start connecting them. In this case, the orange wire goes onto the pulse, which is the inner row here. So now we're going to bring over our leg that we partially assembled, and we're going to connect it as well to the servo headers. Might be a little hard to tell what's going on here because it's so small. Alright, connect that, connect that. So, if your ESP32 is connected, it will set the servos to 0 for like 2 seconds, but then they'll go to like the default standing. So this is where we have to connect our app for the calibration. Set it to 0. So now we can assemble the leg. So make sure all your servos that you're connecting, they're powered. That's very important, okay? So now all the servos are at 0. So we're going to connect the coxa to its servo head hole, whatever you want to call it. So this is important when you connect it because you want to make sure it's aligned with 0 degrees. It might be close, but you might want to readjust it just to make sure you're zeroed. So 0 degrees in this case is going to be like straight out where the leg is pointing. So you can see here that from the body is like 45 degrees off from the rest of it. So you want the rest of the leg to be straight with that. So I'm just going to keep adjusting it. You might have to pull it on and off until it looks good. Also, when you're installing this for the first time, the fit might be really tight, so you might want to like use a heat gun to heat up the part for like maybe like 1 second or something, just enough to like kind of loosen it, and then you fit it onto the servo and it will cool down, and then it will have a nice good fit, just if you can't get it to go on. Okay, so that looks about 0 degrees, right? Okay, so the next part is to connect our femur. Okay, so again, actually we're going to connect our coxa first, just so it doesn't fall off, because I feel like it's going to. So we're going to use one of these little tiny screws. These are called the servo head screws. Okay, make sure it's screwed in there nice and tight. Then we're going to put this connector on. This protects the screw from falling out, because eventually the screw will loosen a bit because it's moving left and right, the servo. So I put this on to prevent the screw from falling out. So even if the screw is loose, at least it's not going to fall out and you'll lose it. Okay, so it should snap into place right there. Okay, now the next part is to connect the femur. So again, we're going to want them at 0 degrees. So in this case, 0 degrees is if the leg is straight out like this. Okay? So when you go to put that femur on, you want to make sure it's as straight as possible, because otherwise your robot will walk funny. Okay, so that's in place. Now again, we have to connect the 2 servo head screws. Alright, so once you got your servo head screws in, you can turn off your robot. You don't need that on anymore. That's assuming, you know, you've installed all the legs. So the next part is the screw covers for the femur. So you can see here there's these 2 holes. This snaps into here. And this will also protect the screws from falling out if they got loose. Next is the coxa swivel connector. So we have this guy and these 2 pins right here. So they snap into place like this. And then this end with the flanges goes around the static body mount, and then this connects to the top of the coxa. You can see here. Should freely allow movement left to right. No resistance. Okay. So at this point, you should have all your servos connected. And your robot should be technically operational at this point, so there's not much left to do. For this demo, we'll just move ahead to the end. Also, for the light bar circuit, I have this JST connector that comes out here. So that makes the light bar disconnectable when we're taking off the top, which is very useful. So just remember this. Next, we're going to take our 6 extra large pins here, and we're going to fit them into the top cover piece. So it's this guy right here. They should snap right in, like so. Okay, so next we're going to snap the top plate on. That's the cover. But first we're going to put the JST connector for the LED in here, as such. And then it should snap into these 6 holes that we have here, ready to go. Make sure they're snapped in all 6. All right. It's mostly assembled. The last thing is to put on the LED light bar. So we have this 3D printed piece. So the LED, just like you can see, here's a slot. It just slides down into it. Let me see. Yeah, like this. And you can see I have the other side of the JST connector already connected. And I have it looped through this little loop here just to keep it intact so it doesn't get ripped off as easily. So, okay, slide it back in. It's a pretty tight fit, so you really got to force it in. Okay, so then that snaps onto the top rows here into these holes like that. Nice and secure. And then we connect our JST connector. So we'll briefly discuss the electronics schematic. Overall, it's pretty simple. We have our servo board here with the servos connected, and what servo headers they should be connected to. And then we have the microcontroller, the LED circuit, the voltage regulator, and the battery. So a more detailed explanation. So we have the USB charger that comes with the battery that I linked in the bill of materials. So this is disconnectable, so this is external to the Spiderbot. Then it's connected via a Dean's connector, that's the special connector that's listed in the bill of materials. Then we have a single pole, single throw switch connected to our voltage regulator. So our voltage regulator, the output's connected to VS1 and ground on the servo controller board. And the 5 volts and ground is also connected to the 5 volts and ground on the ESP32 cam. And it's also connected to the 2-watt 5-volt LED. And here we have our transistor, which is controlled by pin IO4, along with its biasing resistor, 110 ohms. The port IO1, which is also the transmit pin, is connected to the receival pin on the servo controller. So overall, it is a fairly simple schematic. And that was the design from the beginning, was to make this circuit as simple as possible to assemble, which I believe was completed with a 5-volt system in mind. So the voltage regulator powers everything. There's no need for 2 separate voltage regulators, one for 5 volts and then one for 6 volt for the servos. This is MIT App Inventor. So this is the free online website I use to make Android apps. So I use this to make the Spiderbot controller application, which is a very useful app in my opinion. So I just designed the interface here. It's pretty simple. So this is just like a web browser that's set to the IP of the camera stream from the ESP32. And then all of these buttons, they send commands. This is what the website looks like if you are have the project uploaded to MIT Inventor. So you have to make an account first. you would download the project file from the project overview, and then you could edit the app if you want. But of course, if you don't want to edit the app, there's no need to at all. You can just download the APK file onto your Android device from the project overview, and you can just install it, and it should work right away. There should be no problem. But I would like to offer anyone that wants to customize their app should be able to. So once you've uploaded your project, it should look just like this. So you can add more buttons. I'm not going to go into a tutorial on how to use this website because, of course, this is well documented. But say you want to, after you finish editing your app, you would go to Build Android APK, and then you can download the file. So this is the code blocks interface. So this is where you program the app. So I've laid out the code blocks in the exact same orientation as the app itself. So you can see we have our 2 buttons up here, and then our grid of buttons, as well as sliders and more buttons, text box. So if you go back to the blocks, that's exactly how these are laid out. So these buttons right here, they adjust the camera width. These buttons here, they send a letter command, which is decoded on the end of the ESP32. So for example here, the stop button right here, so that sends the letter S. So that's received as the stop command on the Spiderbot. Every command has its own special letter. So for example, strafe right is D, strafe left is A. Then down below, we have more commands. So the calibrate servos, for example. And these are the 2 sliders. So they send a number from 1 to 9. And if it's changing the speed, it sends a P and then a number. And if it's changing the walking height, then it changes a height. Then it sends a H and then a number. And then these just change the button colors when they are clicked on. So they're just for cosmetic only. So before we dive into talking about the code, we're going to talk about this high-level overview of what the code does with relation to the Android app and the ESP32 cam. So in this left side, we have the Android app. So what it does is the user will press a button, right, of course, in the app. And then upon a button press, the Android app sends a UDP packet to the target IP address, which is the ESP32 cam. So this packet is made up of 2 characters. The first character is going to be a letter. It's arbitrary what letter. And then the second character will either be a number from 1 to 9. So if the action, let's say, for example, is walking, it will just send a W character and that's it, because you don't need to send a secondary character, the number with walking. But if we're updating the speed, so let's say S is the speed update, so then it will check what is the second character. So it's like S9. So that says, okay, we need to update the speed, and we're going to update it to the maximum speed, whatever that would be, because 9 would be the highest. If you send an S1, for example, then it would set it to the lowest speed. But that's only for the speed and the walking height, where the second character is used there. So anyway, on the ESP32 cam side, once it sends a packet, the packet will be received, okay? So then once a packet is received, it will check for actions performed only on packet receival. So for example, this would be like toggling the headlight. You don't need to keep toggling the headlight because it's already been done. So if an action is to be performed, send a command string to the servo controller, if applicable. For example, toggle headlight, that doesn't actually send anything to the servo controller. It actually just turns on a pin on the ESP32, which controls the headlight. It will perform continuous action, and then update if a different packet is received. So for example, if the Spiderbot was already walking when the packet was received and it's not changing that state, for example, a different type of command was sent, like toggle the headlight, it will just keep walking. If a new command is sent that's going to overwrite the old one, for example, stop, like it was walking and it's going to stop, okay, then it will switch to that action. So then the flow diagram, it sends the command to the servo controller, and then the ESP32 goes back to listening for packet. And if no packet is received, it will go back updating that continuous action. So I'm going to do a quick walkthrough of the Arduino code that's used here. So this is the main file here. We have 3 files which support the main one. Right here we have a diagram of the leg layout, which is useful because right below is where we have all the servo leg bindings. So these numbers represent the channels on the servo controller. So if you want to modify your Spiderbot, what servo is connected to what channel, this is where you would do it. We have default standing angles. This is pretty important. You can just leave it as is, but this will determine what your Spiderbot will do when it's at a resting state. We have the Wi-Fi SSID and password. So this is what your Spiderbot will show up as when you turn it on in terms of Wi-Fi networks. So I just have it to the default ESP32 Spiderbot and then an easy password. But of course you can customize that to whatever you wish. This is just the setup. And then we have the main loop here. So I'll just briefly explain the logic of what's going on in the loop. So it's constantly checking for a packet. If there was a packet received, then perform functions. So right here in this same if statement, we have functions that are only performed once upon receiving a packet. So for example, turning on the LED, toggling calibration mode, updating the body height or updating the servo speed. We don't need to constantly be doing those, so that's why they're here. Everything outside of the loop is performed based on what is happening. So for example, if we have a command of walk, which is a W, this loop is going to keep checking if the packet is still W, okay? Because only if a new packet is received, then it will update, but otherwise it will keep assuming that same packet that was received. It'll keep doing that action. Because essentially, so it's like, say I send the packet and it's a W, okay? So then it's going to check the code, okay, update this stuff as normal, and then move on. So then it sees is the packet W, then update the walking, and then the loop will run through, and then again it will see no new packet was received, so don't update these, but still the packet was a W, so update again. So it'll keep doing that until a new input is received from the controller. So here we have all the different actions that are performed consistently. So we have, for example, like the stop, the walking, the strafing. So we have a if statement for each action that we would want performed. And then at the bottom here, it will send the serial command to the servo controller after everything has been completed in the loop. So we have our second file here, the ESP32 functions. So these are mostly just functions related to setting up the camera and the web server. I'm not going to go into any detail here because this was mostly taken from a pre-existing library. And then the last file we have here is the Spiderbot functions. So this is where all the low-level Spiderbot functions are contained. So for example, we have toggle LED headlight, toggle calibration mode, update servo speed, update body height, send serial command, aka like sending it to the servo controller. We have update servo speed, movement state transitions, default leg angles, servo positions, multi-servo positions. So this is kind of like a abstraction layer between sending the walking command and then it figuring out what angles need to be applied to what servos based on the current command. And then we have a specific lag relative command. Again, this is another abstraction layer. And then we have a lag one group command, leg group one command, and leg two group command. So again, it takes advantage of symmetry of the spider walking. So that's why we have a lot of like leg group one and leg group two, because the Spiderbot walks like a tripod, because there's always 3 legs on the ground, at least in most of the walking actions. So you can take advantage of the symmetry there, and it really simplifies all of the calculations. And then down below here, we have the actions, or the functions for each action. So for example, this is the walk forward function. So I'll just briefly explain how this works. So if we think back to the loop, when the action gets called, okay? So then it goes into this function, and then it sees how much time has passed. So for example, here, the walking, right? It's a cycle. It will complete some actions in a sequence and then start over again, and then do that actions in the sequence again. Because walking is going to be same, right? Like you take a step forward, you put your other leg forward, then you put the first leg forward, and then it just repeats, right? So the way this works is it checks how much time has passed, and then based on how much time has passed, then select that current action and execute it. So for example, we have 4 action groups here. So action group 1, action group 2, action group 3, action group 4, right? So based on how much time has passed in the period, it will execute one of these 4 actions. So that's kind of the fundamental of how the walking works, or strafing or rotating, whatever it may be. So if you wanted to add a new action, you would just copy one of these functions and then add as many action groups as you need for like steps in your action, whatever it might be. Because for example, we have 4 groups here because it takes 4 distinct actions to complete a full walking cycle. But you could do 2 action groups. You could do 20 action groups. It just depends on what you're trying to achieve. But it has that flexibility of allowing you to like really build out your own custom actions. I'm not sure what else anyone else would come up with, but the fact that you can do that is great, because I would like to see people come up with their own custom actions for sure. And then down below, we just have functions for each action. And that's pretty much it. Of course, you know, I could go into way more detail explaining how everything works, but for the sake of keeping the video brief, that's all you need to know. Another thing to watch out for is make sure the wires of the servos are not getting binded in a part. It is possible for the wire to get stuck and possibly get sheared off. So just keep an eye that it doesn't get stuck and sheared off. Some ideas for expansions onto this build would include adding 2 servos for panning and tilting the ESP32 camera, so the robot could be able to look around, because right now it's stationary to the body. So I think being able to look around the environment would be useful. You can also build custom attachments. So if you look at the light bar, it's actually attached by a pin connector. So you could actually mount your own sensors or electronics to the top of the Spiderbot using the existing pins. I think another improvement would be utilizing inverse kinematics to fully leverage the full 18 degrees of freedom that the Spiderbot has. For this project, I found that it was going to be too complicated to implement inverse kinematics, when a quick and dirty solution of programming the legs would work just fine. But if you were able to implement inverse kinematics, it's much more expandable, and you can really do lifelike movements, which would be very smooth, and you could potentially have much faster movement. But for the purposes of this project, I think the current solution is satisfactory, and that's proven by the videos of the demo earlier. Also, adding a function for the Spiderbot to unflip itself would be a good add. So to do that, you would just need to add a button in the MIT Inventor project, create a new action code, and then add a action in the software with the servo leg angles that would help you unflip your robot. So if you've watched this far, thank you, and you must be pretty interested in building your own Spiderbot. So you should definitely please build the robot. Everything is absolutely free other than buying the parts yourself. I would love to see some people build their robot and share their versions, because that would just be amazing. And I think this is a great project for someone that's looking for an intermediate robotics project. And of course, you can customize the hell out of this thing. That was the whole point of this design. So if you want to add your own custom attachments, I would love to see what people come up with. So thank you for watching.